Before going into this question, I want to remind you of some principles of doing revision. It's not going to help you very much merely watching this video or reading through the memo. You really need to practice yourself. So here's some suggestions for effective revision. Do not practice questions which you firmly know that you can do. Rather select the questions on topics where you know that you will have difficulties. The only time you start practicing full papers is when you are trying to reduce your time taken to do the paper. When you have reached the stage of being able to do all the questions. If you become stuck at a question, yes, watch the video. Then it's vital that you attempt the question yourself, preferably a day later, in order to test your understanding rather than your short-term memory. The very best way to revise math is quality as opposed to quantity. It is more effective to complete fewer revision papers completely and correctly, ultimately without having to refer to help of any form, than to complete as many papers or exercises as possible. I often come across people who say, "Oh, how many revision papers have you done?" "I've done 8. But the point is, it doesn't help to do 8 revision papers if you leave out everything you cannot do. And of course, this goes with what is said to be a Confucius saying, "What I hear I forget, what I see I remember, what I do I understand." And that works very well with any learning you do. That's why this is written rather than just said to you, so that you can look at it and remember. First question, exponential equation. You could treat this the same as any normal equation. So first of all, we need to get rid of the negative exponent. Remember, it's the opposite. If you're differentiating, then you need to bring everything into the numerator if you have separate terms. So there we are. E to the x goes to the denominator because it has negative exponent. Now, normal principles of equation apply. Multiply through by something that cancels out all denominators, this being e to the x. And now we have a quadratic equation. There's the square, there's the first degree, and there's the constant. So we need to factorize. There's the equivalent of this equation using k. Solve the equation. Now at this stage we haven't solved yet because we need to solve for x. So we need to go a step further, and I remind you that in order to do that, if we're going to bring x down to the base, well, down to the number, not the base, this would be confusing, hey? Then we need to go from exponential to logarithmic form. And here's what that really means. If a to the x equals c, then x, the exponent, is equal to log of c to base a. Notice the base in the exponential form is still the base in the log form. And here we have it. X equals log of 3 over 2 to base e. Ln just means log to base e. Or x equals log of 2 to base e. It says exact form, so we're not going to go any further, because if we now evaluate this using calculator, we're going to get an approximation no matter how many decimal places we use. So the intention is for you to leave this as logs. Absolute value. This is a very straightforward question. Often you have to go to the very definition of absolute value, but not in this case. So first of all, we convert the absolute value of 2x plus 3 to plus or minus 2x plus 3. And of course that follows that, therefore, why don't we just convert it to the other side? So 2x plus 3 equals plus or minus brackets 5x minus 2. You can go from the first stage right to that stage in the first line. Don't write unnecessary things, it just takes more time. Now we have to break it into two equations. Our 2x plus 3 equals in both cases, and the positive version of 5x minus 2 and the negative version of it. And solving those equations, we get 5 over 3 and negative 1/7. But remember now that in the case of absolute value equations, we need to test our answers. We need to put our answers back into the equation just to see if they are true. And in fact, that check reveals that negative 1/7 will not work, and it's only 5 over 3. Very quick to see that negative 7th doesn't work. You don't have to do the whole exercise of calculating down to a number. If you put negative 1/7 into here, we're going to end up with a negative value overall. And an absolute value can't equal a negative. Here is a rational inequality. We can't just multiply through by the denominator, remember, because these are variables and we don't know whether they're positive or negative and whether or not we need to flip the greater than or equal to sign. So first of all, I'm going to take the negative out of that, so I have x squared plus 5. It's a bit pesky having to deal with negative x squared, especially in inequalities. Now, I'm taking that absolute value of x plus 3 out because it's greater than or equal to 0, so it can't affect the outcome. The only way these can affect the outcome is if they're changing their signs at a certain x value. Of course, this is all equal to 0, so in many cases an absolute value would still have an answer. If x plus 3 was the numerator, then x equals negative 3 would be included in the answer. But this is denominator, we cannot divide by 0, so the whole one goes out. Times through by negative 1, so we get rid of that negative. So all that happens is we drop the negative there, that sign flips around. Now here's another bracket we're going to drop, and that's x squared plus 5. Because in fact x squared plus 5 is greater than or equal to 5, so we can exclude it as well. It's always positive. So now we're down to simply that fraction. Now we need to factorize the top line. Now we can find out the critical values. Critical values, minus 4, minus 2, 4. And we're going to put them into a table. And then we're going to test to see, take any value less than negative 4, like negative 5, and substitute it into each. You don't have to use a table because quite honestly, you could say, well, if x was negative 5, this would be negative, that would be negative, that would be negative. So overall, negative times negative over a negative would be a negative. So therefore, this region does work. And so on. Infinity there, or undefined, because you cannot divide by a negative. So now this is greater than or equal to 0. So we include the 0 there. So therefore, it's, if we do it in interval notation, we've got negative infinity to negative 4. Notice we exclude the negative infinity because it's a concept, not a number. But we include the 4 because it's all equal to 0. So therefore, we include the negative 4. In this case, we exclude the negative 2 because it's undefined at that value. So it's from negative 2, excluding negative 2, to 4, and we include the 4 because we need them to be negative or 0. And so there are your answers. Complex numbers. So we're given that 2 minus I is the root of the equation. We need to write f of x there. That's a fourth degree expression as a product of two trinomials. Well, with complex numbers, all the coefficients of x terms and the constant are rational. And they're real. So that means we cannot have irrational roots or unreal roots, complex roots. So therefore, we could turn to what we call the complex conjugates, you'll remember. 2 minus I is a root, and therefore 2 plus I must also be a root, complex conjugates. That's the only way it can work to get rid of the I squared. You see, when they multiply together, those numbers, is if you have a difference of squares. So now I'm going to do it two ways, by sum and product of roots, because often it's done that way. It's actually slightly shorter. There's the actual expression. X squared minus the sum of roots x plus the product of roots equals 0 is the equation. So we're going to add the roots. There we are. Sum of roots, product of roots. And if we add those two to add that all up, we get 4. If we multiply those together, we get 4 plus 1, which is 5. So there's one of the trinomials. If we do it as a product of binomials, then we have to say x minus this one times x minus that one. Now we're going to rearrange these and put x minus 2 together. X and minus 2 together, they are separate. Now we have a difference of squares. We square it out, we get x squared minus 4x plus 4 minus r squared. And it simplifies to x squared minus 4x plus 5. Now we're going to find the other trinomial using inspection. We now know the one, so there it is there. We know it has to be an x squared, a quadratic, in order to give us x to the 4. Because it's just 1x to the 4, if we have an x squared there, there must be an x squared there. Because it's a negative 30 and we have plus 5, we need minus 6 there. But this is the questionable term. We're not quite sure, so we'll call it mx, kx, gx, whatever you like. Now, I'm not going to multiply it all out. I'm going to look at just, let's say, equate the terms of x cubed. Because there it's minus 3x cubed. So therefore, x squared times mx gives you mx cubed. And minus 4x times x squared gives you minus 4x cubed. And those two combined must give you the minus 3x cubed there. This gives us m equal to 1. So there we put the 1 instead of m, and there we have our product of trinomials. Now we have to solve f of x equals 0 in complex numbers. So we have those two multiplying together, which means they are equal to 0. We're going to solve this one easily by factorization, but this one we're going to have to use quadratic formula. And I'll leave that to you to do, because it's just a case of applying quadratic formula and simplifying the surge, where square root of negative 1 is r. Well, in fact, you don't even have to do that, hey, because we have the roots of that equation in the first place. Yes, I would be wasting my time going quadratic formula. Add minus 3 or plus 2. 1.3. Quantity defined a new type of complex number called the quantity number. It has the property that the imaginary part of z equals twice the real part of z. Just to remind you, MA plus BI is the B, RE A plus BI is the A. It's the real part, A. It's the imaginary part or unreal part, B. In other words, a quantity number, Z, is of the form Z equals A plus 2AI. Have a look. There's the real part, and the imaginary part is twice the real part, 2A. Prove that for all quantity numbers, Z over Z star, that there means conjugate, the conjugate of Z. So if that is A plus 2I, this will be A minus 2I. So we don't have to let this flummox us. We can just substitute in and see what happens. Let's put A plus 2I over A minus 2I into it. There we are, like that. And we're going to simplify this. Of course, you notice that we could actually take out the A and cancel it. But let's multiply it out first. So we're going to change into, we're going to get rid of the complex number in the denominator by multiplying by the difference of squares, and means we need the same on the top line, so we're really multiplying by 1. There's our product. R squared is -1, so we end up with a squared minus 4a squared, which is minus 3a squared. And now we can simplify down, getting rid of the a squareds. There it is there. And that's what we have to prove.